In Chapter 9, Section 1, we do some more probability distribution investigations, taking it a little further, and we're going to talk about what we call expected value as well from this section. First of all, let's do some definitions. A random variable is a function that assigns a real number to each outcome. So a function that assigns a real number to each outcome in an experiment. So when you see the book or my math lab talk about a random variable, we are just talking about being able to discuss the outcomes in an experiment. Our probability distribution is a table that lists all of the possible outcomes, so that sample space, with their probabilities. And finally, a histogram. A histogram is like a bar graph, but with a bar graph, you are really looking at frequencies of what we call discrete or countable variables, things like the number of people. Well, there's either one person or two people or three people. There's never going to be 1.75 people in the room. With a histogram, we are talking about measurable, continuous variables. So a histogram is a special bar graph that allows us to represent frequencies of continuous or measurable values. Things like age. You aren't either 49 or 50 years old. You are on a continuous scale of aging, depending on how exact. Your weight, you don't always weigh a full number of pounds. There's ounces in between and parts of ounces in between that. So a special bar graph for continuous variables, goodness. The difference between a bar graph and a histogram, with a histogram, the bars are going to touch rather than have spaces between the bars because our values are continuous. There's no spaceable or a difference between the values. They just move on a continuously progressive scale. The bars should always be the same width. And the height of the bars is determined by either the frequency or the probability. So the heights of the bars are determined by the probability of that outcome. Okay, first example here. We're going to give the theoretical probability distribution for the number of heads showing up when two coins are tossed. So we know that each fair coin is going to have heads on one side, tails on the other. If we're tossing two coins, then we've got more possible outcomes. Our random variable x is going to be the number of heads. That is the event that we're interested in. So x represents the number of heads. So let's figure out what the sample space would be, and we're going to use two different ways. We're going to use a tree diagram and an organized list. All right, tree diagram first. Our first branch represents that first coin, and that first coin can either be heads or tails. Now the second coin has the same two options. Excuse me. And the outcome of the two tosses or the two coins together is determined by what happens on the first toss as well as what happens on the second toss. I can see that I've got 4 different branches on my tree. There are 4 total outcomes that are possible. Either I can have heads on both coins, both tosses. I could have heads on the first coin, tails on the second. I could have tails on the first, heads on the second. Or both of them could come up tails. So there's my tree diagram, here's my organized list. I see that this number of outcomes in my sample space is 4, no matter which way I look at it. I have 4 different outcomes in my sample space. Now the variable that we're interested in is how many heads there are on those 2 tosses. So when I do my probability distribution and I set up my table, heads represents, or excuse me, X represents the number of heads, and we're interested in that probability of X. Well, when I look at my list, or I look at each branch of my tree, I see that I could end up with 0 heads. I could get a head on 1 coin, or I could have heads on both coins. So those are the only possible outcomes. I could have 0 heads, I could have 1 head show up on the 2 coins, or I could have both. Out of my 4 outcomes, there's only 1 of them where I don't get heads on either coin. So that is 1/4 of the sample space, 1 out of 4. There are 2 ways I could get 1 of the 2 coins lands on heads, so that's 2 out of 4, which is going to simplify to 1/2. Or that 4th outcome, when I have 2 heads, that's 1 out of 4 possibilities in my sample space. Now, we've talked about different ways to represent probabilities. If we're going to be working with them, we don't simplify and put our fraction in lowest terms, but we can simplify and leave it as a fraction in lowest terms. The other option is to turn it into a decimal. 1 divided by 4 is 0.25. So the probability of getting 0 heads is 0.25. The probability of getting 1 head is 0.5. And the probability of getting 2 heads on both coins is 0.25. If I add those probabilities together, I get the entire sample space represented. I get a probability of 1. It's a kind of a quick check to make sure that I did things correctly. So this is my probability distribution table. Now we're going to do a histogram. And as I said, a histogram is really just a bar graph. So we're going to set up a bar graph. My outcomes is those number of heads on the 2 coins, and I know that there are 3 different possible outcomes. I've got 0, 1, or 2, and I've got my probabilities are going to need to go up the y-axis. So I've got fractions in here. 1 would be the entire thing. If we want to go all the way up to 1, we can, but my largest probability is 0.5. I'm going to choose to count by tenths and say 1/10, 2/10, 3/10, 4/10, 5/10, 6, 7, 8, and that's more than far enough. So 1/10, 0.2, 0.3, 0.4, 0.5. Okay. Well, the probability of getting 0 heads, and let's make those bars even width, the probability of getting 0 heads is 0.25. So that probability is going to be right here. There's my probability of getting 0 heads. The probability of getting 1 out of the 2 that lands on heads is 0.5, so that bar is going to be twice as tall. It's going to go up to 0.5. It's going to be just exactly as wide. And then the probability of getting 2 heads is the same as the probability of getting 1. You can see how our histogram lines up. Okay, let's look at the next page. We're going to do some application problems here. One question asked in the 2016 General Social Survey had to do with daily hours of TV viewing. The following probability distribution and histogram were created from the results. So X is going to be my random variable. It represents the number of daily hours of TV viewing. So I see that we went from 0 hours a day up to 6 hours a day. And then we have our probabilities that someone answered that number. As I look through, I see that most people, my highest probability, said that they watch about 2 hours a day. And so when I come over here, I see that that is represented by the highest of my bars in my histogram. What is the sum of this probability line? Well, if I plug this into my calculator and my probability distribution has been well done, that sum should be 1 because it represents all the possible outcomes. What is the probability that a respondent spent 1 or more hours watching TV? Well, 1 or more hours watching TV is going to be all of these probabilities. So to figure out that probability where this is my event, that the respondent spent 1 or more hours watching TV, the probability of that event, I have a couple of options. I can either add up all of these probabilities, or I could say, you know what, this entire thing is equal to 1, and I'm interested in all the probabilities except this one. So I could start with my total and subtract the thing that I don't want, and I see that the probability that a respondent said they watched 1 or more hours of television each day is about 0.9. So I used the complement. This is the event I'm interested in. This is everything else. It's easier for me to figure out the complement, that everything else part, and just subtract it from 1. Okay, expected value. Suppose that that random variable x can take on all these different values, and that the probabilities that these values occur are given as p sub 1, p sub 2, p sub 3, etc. Then the expected value of that random variable can be found by adding up the value of each of the individual probabilities. Now, we use expected value when we're interested in finding the balance point or the mean or the average for the random variable, and it also allows us to determine if a game is considered fair or favors one player or the other. So let's go back to our TV viewing example and find the expected value by finding the average number of hours watched as reported by those who are surveyed. When we find the expected value, we assign a weight to each of our values of x, and the weight is equal to the probability. So I have 1, 2, 3, 4, 5, 6, 7 different outcomes. To find the expected value, or the weighted mean, I'm going to multiply each outcome by its probability. So the outcome 0 hours of TV viewing, it has a probability of 0.1. The outcome of 1 hour of TV viewing has a probability of 0.21. And if you look back up there at your table, you can see that I am just working my way along the table, and I cannot write and talk at the same time today. 2 hours of TV viewing was my highest probability. Then I've got 3 hours at 0.17. The probability that someone said they watched 4 hours is 0.13, and I'm just getting these from my table at the top of the page. And then finally, the most that people said they watched TV is 6 hours a day. And the probabilities of having someone answer 5 or 6 are almost but not quite the same. Now when I plug this all into my calculator, I get an expected value, or a mean, or a balance point or average, depending on how you want to term it, of 2.4 hours of television viewing. Now that's a lot to plug in and make sure that you get right in your calculator, right? So we have to be careful and make sure we do a good job with that. Okay, so that's how we find expected value. We're going to do 3 more examples, 3 more application type problems together. Each day, Lynn and Tanisha toss a coin to see who buys coffee. Coffee costs $1.75 a cup. So one tosses the coin while the other calls the outcome. If the person who calls the outcome is correct, that means the other person has to buy the coffee. If the person calling the outcome is wrong, then they have to buy their own coffee and coffee for the other person. So instead of buying 1 cup of coffee, you're going to buy 2 cups of coffee, or you're not going to have to buy coffee that day. Use a tree diagram to find the sample space and probabilities, and then calculate the expected value for Lynn. Is this a fair way to decide who buys? Does it come out even so that you don't make money or lose money off of it, basically. All right, so there are two different things going on. Somebody is going to call the outcome while someone else tosses the coin. And the person who calls the outcome is either going to call heads or tails. The person who tosses the coin is going to toss a coin that comes up either heads or tails. So from the call to the toss, we have 4 different branches, so we've got 4 different outcomes. So either they're both heads and they match, or one is heads and one is tails. The call is heads, the toss lands on tails. Or the call is for tails and the toss lands on heads. Or they could match in that the person calling said tails and it did land on tails. So, how often, what is the probability that the person calling it is correct? Well, if the person calls it is correct, that means they called the same as the toss landed. So 2 out of 4 outcomes, or 1/2, or 0.5, is the probability that the person calls it correctly. What about the probability that they're going to call it wrong? Well, that's the other 2, right? They call tails and it comes down heads, or they call heads and it comes down tails. We have the same probability for that outcome. Now we're going to check our expected value to make sure that means what we think it means. My expected value is that I either save $1.75, right? I save $1.75, and that's going to happen half the time. Or that I spend an extra $1.75 because I have to buy a second cup of coffee, and that's going to happen half the time. So either I save my $1.75 because the other person buys the coffee, or I have to spend an extra $1.75 because I got to buy her coffee. Well, if I multiply this and then multiply this and find the difference, they're the same thing, right? So I can plug it into my calculator, or I can reason through that my expected value for this bet is $0, which means it is a fair game. It's a fair bet. They're just having fun. They're equally likely to just take turns buying the coffee. Okay, number 5. A local symphony decides to raise money by raffling off 5 prizes. So we've got 5 different prizes in the raffle. We've got 1 pair of concert box seats worth $400. We've got 2 prizes of a dinner for 2 worth $100, and 2 prizes of drinks vouchers for a venue worth $40. So we've got 5 different prizes. The first one's worth $400, 2 of them are worth $100, and 2 of them are worth $40. A total of 2,000 tickets are sold at $1 each. We're going to set up a probability distribution and use it to figure out the expected value of winning for a person who buys just 1 ticket. So X is that expected value of winning. Okay, so we've got 3 different types of prizes, right? We've got the box seats, we've got dinner, we've got those drinks vouchers, but really most people who buy a ticket aren't going to win anything. Only 5 people are going to win, and there are 2,000 tickets sold. So the expected value is X. That's how much money we come out ahead. Well, my ticket costs $1, so if I win the box seats, they're worth $400, but I spent $1. So my expected outcome, my expected value, is a gain of $399 worth. My dinner, if I win the dinner, I come out ahead by about $99, right? Because my ticket cost $1. If I get the drinks voucher, I come out ahead by $39 worth of drinks because I spent $1 on the ticket. And if I don't win, I'm out my $1. The ticket was just a donation, and I lost $1 value for it. So that's the expected outcomes. What's the probability of each outcome? Well, there's one pair of box seats. Out of 2,000 tickets sold, one person is going to get those. There are 2 dinner prizes, so out of 2,000 tickets sold, 2 people are going to get those. 2 people out of 2,000 will get the drinks voucher, and that's 5 tickets, so the other 1,995 tickets are not winning tickets. Let's do our expected value calculation. We're going to take each value and multiply it times that probability. Now, you can plug into your calculator wherever you want to plug into your calculator. Just remember, we don't round before the end. I could simplify that, right? 2 over 2,000 is 1 over 1,000. I can leave it 2 over 2,000. It doesn't matter. Either way, oops, there I got to talking and writing and they didn't mix. Either way, as long as I use my order of operations right, we're okay. So 2 drink vouchers, so that would be again 1 over 1,000 or 2 over 2,000 minus 1 times the vast majority of the tickets, because most of them are not winning tickets. When you plug all this into your calculator, assuming you use correct order of operations, you come out with a negative expected value of a negative 66 cents. Now, no one spent 66 cents on a ticket. You either spent $1 on a ticket, but the average expected outcome on average loss is 66 cents. So this is not a fair game, which we don't expect it to be, right? Anytime you do a raffle, you expect that there's a bunch of tickets sold and only a few of them are going to win a prize. The average loss is about 66 cents. Nobody lost 66 cents. Everyone either lost $1 per ticket or they won a prize and they had gain of value. All right, last one we're going to do together on the video. Remember, we talked about an American roulette wheel. An American roulette wheel has 38 slots. 2 of them are green, the 0, 0. Then we have numbers 1 through 36, 1 through 36. Half of those numbers are red, half of those numbers are black. A simple way to wager is to bet $1 on red. If the marble lands on a red slot, you double your money. And if not, you lose your bet. You lose your $1. So on average, what does the casino expect for bets like this? So, our random variable x, we either win or we lose. So if you bet $1, you're either going to win another $1 back because you double your money, or you lose that $1 that you bet. So you either gain an extra $1 or you lose the $1 you bet. What's the probability of this happening? Well, out of those 38 slots, we're betting on red. 18 of them are red because 2 are green and half of the other 36 are red. So half of 36 is 18. So 18 out of 38 slots are going to be a red winning bet. All right. The other, what is left? 20? The other 20 are going to be losing bets. So what does, oh guys, hold on, I've got computer issues here. We make sure that we haven't lost you. What happens, okay, looks like we're good. What happens with our expected outcome here? What does the casino expect to happen? Well, my expected outcome, I either gain $1 18/38 of the time, or I lose $1 20/38 of the time. And I can look at that because the value is opposite, +1 or -1. I can look at this and see my larger fraction is going to be the negative value. So I expect a negative outcome. If I plug this into my calculator, you should get a negative 53 cents. So that's a 53-cent loss on average. On average, make sure we interpret our results. A player expects to lose 53 cents a bet. So is this a fair game? Well, no, it's not a fair game, but it's a casino game. Everything favors the house in a casino or they couldn't have the business, right? So on average, when we interpret our answer, on average, a player expects to lose about 53 cents per bet. And they don't ever lose 53 cents because the bet's $1. You either win an extra $1 back because you doubled your money or you lost that $1. But this is an on average.